Okay, we already defined the integral of f with respect to the gamma. And now let's try to evaluate for certain special type of gamma. So that's evaluate this integral. That's a theorem 1.9. What is a special? What the special means here? Special means this gamma is either piecewise, either smooth or piecewise smooth. Okay, so if gamma is piecewise smooth, and f from AB to C is continuous. Okay, then this integral from A to B f d gamma, it is actually equal to the integral from A to B f t dt gamma prime of t dt. So this left hand side is that number I in the previous theorem. We use a lot of analysis to show it. First, we use analysis to show the existence of I. Or when I say analysis, I mean the counter theorem. You have a sequence of a compact set. One is inside the other one, and they shrink to the diameter shrink to 0. Then this I exists. It's unique, and then we prove that the sequence will converge to I, right? The not sequence, the net will converge to I. The epsilon m definition. Okay, and this right hand side is a calculus. The Riemann integral. Okay, so we're going to show that this I literally is equal to this value. The value is the integral defined in the calculus. And gamma is piecewise smooth. Piecewise smooth is this part is smooth, that part is smooth, that part is smooth. So we're going to only assume gamma is smooth, and we integrate over this piece, and then over the next piece, over the next smooth piece, and add them together. We have additivity about the domain. So inside the proof, we only assume gamma is smooth. So without loss of generality, we assume that gamma is smooth. So we have a smooth curve. Well, the integral, remember that I is the sigma f tau k gamma tk minus gamma tk minus 1 k from 1 to n, and I minus this ups value less than epsilon. So here, whenever you see ups value, it means the modulus of a complex number. And when the modulus less than epsilon, so it's equivalent to the real and imaginary part are both less than epsilon, but the epsilon will be different. Let's put epsilon prime, and the imaginary part is less epsilon double prime. Okay, so epsilon prime, epsilon double prime converge to approach 0. Then it implies epsilon. You will imply this. If epsilon prime and epsilon double prime are sufficiently small, you can get this modulus less than epsilon. If this modulus is less than epsilon, then epsilon prime is epsilon, and epsilon double prime is also epsilon. So because of this separate real and imaginary part, we can also assume that gamma will map AB to R, right? It's like we only consider the real part first time and the imaginary part the second time, right? Okay, so that's our assumption. We take the value of gamma in the real part, in the real numbers. All right, So remember that we have two integrals given epsilon greater than 0. And for the left hand side, there is a delta greater than 0, such that if the partition, which is a equal to t0 less than t1 less than tn equal to b, you have this partition with the norm of a p less than delta, then we have this I. Remember, I is this integral from a to b f d gamma minus sigma, this part, k from 1 to n, f tau k gamma tk minus gamma tk minus 1 will be less than, because later we're going to use triangle inequality, so here we put 1/2 epsilon. Okay, so this is the result we just proved before the theorem. And then we go back to the Riemann integral in the calculus. For the same epsilon, there's another delta, then we assume we choose a minimum delta. So we still use the same delta so that this integral, the Riemann integral ft gamma prime of t dt minus the Riemann sum f tau k, the gamma prime of tau k and tk minus 1, also less than 1/2, for any selection of a tau k inside tk minus 1 and the tk. Okay, so for whatever choice sample point, you always have these two inequalities. So this is just a translation of left hand side and right hand side separately. So far we do not connect them. Okay, so at this moment we do not connect them. And then let's try to connect them. The connection is this smooth gamma. Gamma is smooth. Smooth differentiable derivative is continuous. And gamma maps AB to R. It's a real value. Real valued differentiable function has mean value theorem by MVT, mean value theorem, over each interval tk minus 1 and the tk. There is a tau k. Over this, there's a tau k inside tk minus 1 and tk with, what is the mean value theorem? The gamma tk minus gamma tk minus 1 over tk minus 1 is equal to gamma prime of tau k, right? This is exactly the mean value theorem. So if we move this denominator to the other side, what we have, i.e. gamma tk minus gamma tk minus 1 is equal to gamma prime of tau k tk minus 1. So you see, this is exactly here. And this left hand side is this difference. That is a connection. This connection is built up by the mean value theorem. And this tau k is not random. It's related to gamma prime and tk minus 1 tk. Okay? But here, this tau k can be randomly chosen inside this interval. So in the above inequalities, we choose tau k as in the MVT, mean value theorem. So you have tau k here, you have tau k here. We abuse the notation because tau k can be anything. So we just choose the same symbol. But actually, this part, we should use tau k prime And this part we should use possibly Tokay double prime because they are totally independent, no relation. But just to save the notation, so we use the same Tokay. But since they are random, so in those two inequalities, we choose the same Tokay as the Tokay in the MVT. MVT, this Tokay is not random. So we first use MVT to get the Tokay, and then we apply this Tokay in those two inequalities. All right? Then we have the integral from a to b ft gamma minus integral from a to b ft gamma prime t dt. We're going to insert this one. Insert minuses and pluses. Pluses becomes a minus minus. Okay, so it's less than or equal to integral ab ft gamma minus this stuff, k from 1 to n, f tau k gamma tk minus gamma tk minus 1. Okay, and plus integral from ab ft gamma prime of t dt minus sigma k from 1 to n, f tau k gamma prime of tau k tk minus 1, right? This is triangle inequality. And remember that inside the triangle inequality, we actually use this one. A minus b, we insert subtraction a quantity and add. Add means subtract a negative same quantity. And then you factor out the negative sign, it becomes this number minus this number. So it's less than epsilon. So we are done, right? Because this is a fixed difference, positive. It's less than arbitrary given positive number, so this has to be 0. Okay, so if you have a very nice gamma, at least piecewise smooth, then we can calculate this integral, the integral of f with respect to gamma, based on the regular calculus, regular Riemann integral. And the proof only covers a special case. We assume gamma is smooth, and we assume gamma take a real value. But it does not lose the generality. Also, this condition is useful because only for the real valued differentiable function we have MVT. If it's not a real value, we cannot apply the MVT. All right? So this is a theorem 1.19. 1.19. Okay, now let's study a little bit vocabulary and the geometry. Well, gamma from interval AB to C. Gamma is from interval AB to C. And this image set, the set gamma of T in C, here T belongs to AB. This image is called the trace of gamma. So, well, this name is not a universal name. For different textbook, you may see the different name for this image. So you need to understand, or you need to remember what the geometric meaning. The trace is just this set, like the path or stuff. Later you will see another word about path. But anyway, so trace is just image set. And it's denoted by braces gamma, okay? Braces gamma. And because AB is a compact set, remember the image, the continuous image. the continuous image of compact sets is compact. Okay, the continuous image of compact set is compact, so we know that this trace of gamma is always compact. In the Euclidean space, compact means closed and bounded. All right, and gamma. Remember, we noticed that gamma has a property called bounded variation. So if gamma is a function of bounded variation, then we call gamma is called a rectifiable path. See, there's another one. Basically, we want to emphasize it is a rectifiable path. Rectifiable path means you can find the length. Okay? So rectifiable, bounded variation, you have total bond. So gamma is rectifiable if gamma has a finite length, and its length is the total variation of gamma. The length is total variation of gamma, and we know that the total variation of gamma is given by the integral from a to b modulus of gamma prime of t dt. Right? So that's the stuff we know. So we already have trace. Trace is image set. Rectifiable path if you have bounded variation. Rectifiable just means finite length, and the length formula for the piecewise smooth function we can define. We can calculate by this because we do have the derivative. Right? We do have the derivative. Okay. So now let's continue this image, this graph. From this complex plane, we can define analytic function. Assume you have certain open set containing this trace, and over this open set, there's an analytic function f, or the continuous function f, at least f continuous. It maps this open set to another set. Okay. So the continuous image of an open set may not be open. Constant function will map arbitrary set to a closed set, right? So, okay. So if gamma from AB to C is a rectifiable path, with the trace containing certain open set inside C, and F is from E to another complex plane C. It's continuous. All right. Then what we have? You see, we can compose gamma with F. Then F composed with gamma, it becomes a continuous map from AB to C. Is also continuous. The composite function of continuous function is still continuous. All right? So be careful. In this moment, this F is not directly defined over AB. You have to compose F with gamma, and then this composite function becomes defined over AB. And in this sense, remember the previous stuff. What is this f d gamma? F is from AB to C. Gamma is also from AB to C, right? That's the definition of a integral with respect to gamma. In this moment, what we have AB and C. Gamma is this way, and you have a trace here, and then you have F, so it may be defined. It may be mapped to this part. So actually, technically, the F circle gamma has different image set. It's in a different complex plane. Gamma is in this complex plane. F composed gamma is in another complex plane. But because they are the same complex plane, so because they are both complex plane, so we can understand them as in the same complex plane. So you see, we can apply the previous definition to define another integration. So if gamma from AB to C, if gamma is from AB to C is a rectifiable path. Rectifiable path just means it's continuous with bounded variation. And F is a function defined and continuous on the trace of gamma. So at least we need the definition of F over this image. Outside the image, it may or may not be defined. It doesn't matter. We don't use them. Okay, so continuous on the trace of gamma. Then the line integral. So there's a name, line integral of F along gamma, along the image of gamma, because F is defined over the image, is from A to B. Then we are going to apply the previous one. So F circle gamma, D gamma. F circle gamma, D gamma, because F circle gamma is defined over AB, D gamma. And if you want to emphasize the variable, in the book they have F circle gamma T, D gamma T, but it's not necessary. And we say it's a line integral because it's the function F is defined over this curve, okay? And okay, there's another way to write it. This line integral is also denoted by what? You see, F is you are going to integrate F along gamma, so it's F along gamma. And the gamma T is a complex number, so it's a gamma T, Z, right? And gamma T is a complex number, dz, but you only consider this Z over the image set. This is point Z, whatever point on the graph. So you may see the integral of F along gamma or Fz dz along gamma, the same thing. But they both go back to this definition. Of course, if this gamma is at least piecewise smooth, if gamma is piecewise smooth, then what is the integral of F along gamma? It is actually integral from A to B, F of gamma of T times gamma prime of t and times dt. Remember that this is a theorem 1.19, 1.9, theorem 1.9, right? Just move this gamma forward, it becomes gamma prime. D gamma is gamma prime. Okay, and this is our line integral. This is our calculus. All right. So for example, let's see some example. A simple example. Gamma. The closed interval AB is 0 to pi. Whenever you see 0 to pi, you will imagine the trigonometric functions. And in the complex plane, complex analysis, trigonometric functions also relate to the exponential function. So gamma of t is EIT. EIT. This is actually the unit circle. The trace is unit circle. The trace of gamma is the unit circle. So actually, this is gamma of t. What is t? T is this angle. Angle use radian, so gamma t is EIT. Okay, and then we define f. F from c without 0 to c is defined by f of z is a reciprocal function, 1 over z. 1 over z. Of course, z is not 0. And this one is differentiable, then let's check, let's compute the f along gamma. Remember how we do it. 0 to pi AB. F gamma t, 1 over EIT, right? 1 over EIT. Gamma prime, what is gamma prime here? Gamma prime is IEIT dt. IEIT dt. And you cancel EIT. Remember, EIT is never 0. You only have I. You integrate I along 0 to pi is a 2 pi I. Okay, that's a simple computation. And now let's try to do another one. So we do not use this reciprocal function. We use the power function. Any positive integer, any natural number. Natural number, of course, is greater than 1, 2, 3, 4. Well, okay, just use power. Okay, then let's see the integral of f along the same circle, unit circle. This is counterclockwise. T is this way, go this way. So it's 0 to pi. Z is EIT, so it's EIMT. And the gamma prime is IEIT dt. So I, you move I forward, it's I integral 0 to pi EIM plus 1 t dt. Well, what is antiderivative EIM plus 1t? This is just a plain Riemann integral. So you can find antiderivative is 1 over m plus 1 EIM plus 1t from 0 to 2 pi. Or you can follow the computation from the textbook. You write EIT as a cosine t plus I sine t and integrate 2 parts, the same thing. This I is used so that you don't see this I, you only get m plus 1. Okay, and EIM plus 1 2 pi minus EIM m plus 1 times 0. We know this one is equal to 1. We also know this one is equal to 1. 1 minus 1 is 0, so this becomes 0. Okay, so the whole computation, check here, check this computation. This computation you really, well, let's see what we have. Yes, this computation has one requirement, only one requirement. M plus 1 cannot be 0. If m plus 1 is 0, then there's no such denominator, right? So actually this part, we can take any natural number, not natural, any integer but not negative 1. So actually m can be any integer not equal to negative 1. Negative 1 corresponds to this 1 over z. Actually, we separately discuss this special case, z to the power negative 1. If m is not negative 1, then this computation always gave us 0. So if we summarize it, for the power function, integer power function, we do not discuss the fraction or stuff, because for the fraction you have to cut the plane. It is not defined over the whole trace of gamma. So we get the integral of f along gamma is equal to 2 pi I if m is equal to negative 1, 0 if m is not equal to negative 1. Here f of z is z to mth power. And of course gamma is this unit circle. Alright, so that's the stuff. Okay, let's stop this video at this moment. We will continue the lecture in the next video. The lecture is not done. Okay, thank you very much.